In this next section, we are going to discuss accelerating systems. So when we have an accelerating system, the net force does not equal 0 in one or more directions. Now, mind you, you could have a situation where you're accelerating in the x direction and therefore have a force net in the x direction, but you're still at rest in the y. So you're not moving up and down, you're only moving left or right. So sometimes you only have an acceleration in one or more directions. So remember, a net force that's something other than 0 leads to an acceleration, which leads to then a change in velocity. Alright, so in this example problem, we have student A applying a force of 50 newtons in the positive x direction to a box with a 20 kilogram mass on a horizontal surface. Student B is pulling a rope attached to the box with a force of 25 newtons at an angle of 55 degrees above the positive x-axis. Ignoring friction, since we haven't talked about friction yet, what is the acceleration in the box in the x direction? What is the normal force on the box? Alright, so step 1 is to pick an object. So since all of these forces can be applied to the box, and we want to know the acceleration in the box and the force normal on the box, it's a pretty good indication that we should sum forces on the box. Now let's go back through our problem and look for all the forces. So we have student A applying a force of 50 newtons in the positive x direction. So that tells me that there is a force applied in the positive x direction along a horizontal surface. So that tells me that there is a force normal, and the surface is horizontal, so that means that the force normal must be vertical, or in the positive y direction. The box also has mass, which tells me that we have a force of gravity in the negative y direction. Additionally, we have student B pulling on a rope attached to the box. And so therefore there's a force due to tension, and it's at an angle above the positive x-axis. So that tells me that we're looking at a force of tension that is positive x, positive y. See, we're told to ignore friction, and so I think that's it. Alright, so step 3 here is going to be to draw a free body diagram. So we have force normal in the positive y, force due to gravity in the negative y. We have a force applied in the positive x, and then we have a force due to tension in this first quadrant. Alright, so step 4 now is going to be to write Newton's second law in the x and then in the y. So I always start with the x, it's just a habit. So we have force applied, and then the x component of the force due to tension. And that's going to equal mass times acceleration in the x. And then in the y direction, we're going to have force normal minus force of gravity plus the force due to tension in the y direction. So remember that force due to tension has an x component and a y component to it. So this is why we learned the component method before we talked about force. Alright, so let's solve this problem, because our unknown is our acceleration in the x and our force normal. So now that we've applied Newton's second law, we have equations that contain our unknowns. So we know the force applied is the 50 newtons that's given in the problem, but we have force of tension in just the x direction. So if I look at my free body diagram, the x component is adjacent to the angle given. So that means I can plug in force of tension in, well, not the x anymore, because I'm going to replace the in the x with the cosine of theta. Alright, then the force of tension is given in the problem is 25 newtons, and the angle is given in the problem. And this time, we want to know what the acceleration in the x direction is. And there's no indication that we're in equilibrium, so that means our acceleration in the x is not 0. It's a number we're looking for. So I can plug in the 20 kilograms given in the problem, and then I can solve for the acceleration in the x direction. So we get 3.22 meters per second squared. And don't worry, I did that in my calculator ahead of time. I cannot do math that fast in my head. Alright, so that is part A. Now we need to do part B. We need to find the force normal. Alright, so our force normals are unknown, so we can't replace it with anything. Let's see, we're given mass or weight. It's in kilograms, so we're given mass, so I need to replace this with m times g. And since the force of tension in the y is opposite of the angle provided, I'm going to use sine, so force of tension times the sine of theta. And in this case, it's being pulled along a horizontal surface, so we're not moving in the y direction. So our acceleration in the y is going to be 0. So I can sub in 20 kilograms times 9.8 meters per second squared. Remember, we already took care of the minus sign by making the force negative. And then we have 25 newtons times the sine of 55 degrees, and that's going to sum to 0. So my force normal is going to equal 176 newtons. So this gives me another chance to remind you that the force normal is not equal to the force of gravity, because now there's an additional component of a force. So because the rope is pulling up a little bit on the box, that lessens the amount of force that the surface has to push up with to counteract the weight. So the force normal is less than it would be if that rope wasn't there.